Welcome to Talkin' Science, where we dive into the latest news from space and science. Associate Professor Neeraj Sharma from the University of New South Wales is here to discuss a very exciting discovery. Neeraj, thanks for your time.
My pleasure, Matt.
Well, before we get into it, a quick reminder that we can get behind-the-scenes goss and early access to all Trekzone podcasts by becoming a member today. Click the join button on any Trekzone video on YouTube, go to the Trekzone/support, or put your phone up to the QR code that is on screen throughout the show. Professor, can you tell us exactly what you and your team have discovered?
So we've discovered a relatively cool material which accidentally, actually, which doesn't expand or contract as a function of a very large temperature range. So very close to absolute zero, all the way up to 1400 Kelvin, right? So about 1200 degrees Celsius or thereabouts. And it's really interesting because when you sort of look at all the other materials that are out there, it stays the same volume, right? And you can imagine if you go over a road, right, there is little barriers in the road where the concrete is allowed to expand and contract, right? And all of a sudden, because of heat, right? Because as it gets hotter, things expand. As it gets cooler, things contract typically, right? And so this material stays the same as it gets hotter and colder, but over a phenomenal temperature range. So it's quite interesting, and it's also quite thought-provoking from the chemistry point of view. Is how is it doing it? What are the atoms doing? How are they juggling around to make this happen? And so it's like a concerted movement of all the atoms, and that's giving you the zero thermal expansion.
Now, as I understand it, the discovery was a bit of a happenstance. You weren't specifically looking for a thermally stable material.
No, we were actually, a lot of my group works on battery materials and trying to develop new battery materials. And these materials are particularly nice because they've got nice holes in them, right? Nice voids in them, so you can put ions in and out, like in a battery, like a lithium-ion battery. You put lithium in and out, and it's a really nice structure for that. And then we were looking at different compositions, and we found that this one here is actually a sweet spot in terms of thermal expansion and contraction. And so we were trying to use it for a battery, but we ended up finding its own special property, I guess, or its unique property. We've also tried it in a battery, not so good a battery material, but that's what research is.
Well, materials with zero expansion are used in high-precision mechanical instruments, control mechanisms, aerospace components, and medical implants, places where stability at varying temperatures is critical. How exactly do you measure its performance from minus 269 degrees to 1126 degrees Celsius?
So this is okay. Where do I start? Right. So what we did is there's two things that you have to consider, right? The first one is if you've got a bulk sample, so like a pellet or like an engine part, right? And you measure it expanding and contracting, and so that's often called dilation, right? Or dilometry. What we did was we actually used a powder of it, and we looked at it using neutrons or neutron diffraction. And what we can do there is we have a little fridge that goes down to 4 Kelvin. So essentially what you do is you cool it with helium, so liquid helium, and you make it a gaseous helium, and that goes down to about 4 Kelvin, 4.2 Kelvin or thereabouts. And then you take it up to room temperature, and so you slowly warm it up, and you measure its atomic structure, so where all the atoms are, using a technique called diffraction. And then we switch it over to a furnace, and the furnace basically takes it all the way up to, we took it up to about 1500 degrees Kelvin, and we ended up melting the top of the sample holder, and that was a bit of an accident. But anyway, that was actually I think the material reacted with the sample holder and the top of the sample holder, and it sort of fell off. But so that's why we were good to about 1120 degrees Celsius, but not much higher than that. But yeah, that's we were basically like, how far can we go? We just kept going.
Well, and that's exactly how you know the temperature range.
It's a cool experiment. Yeah, exactly right.
Well, the heat applied to the material is absorbed. How does it manage to do that at such extremes?
You can imagine if you go down to low temperature, you're basically freezing it out, right? Imagine water, and you're freezing water right into ice, right? Same sort of thing. So you're freezing all the motions of the atoms. What I said before about this particular atomic structure, or where all the atoms are located, there's lots of voids. So if you imagine there's lots of voids, and so what it does is as it heats up, it crumples a little bit. So in order to maintain its volume, it doesn't expand out, it expands and crumples. And so that keeps everything in the same volume, right? Now, I should say it's three-dimensional space, so you have X, Y, and Z. One of these axes increases a little bit, the other two decreases a little bit. So that's how it keeps its volume, but it keeps it the same. So it's sort of I talk to the next atom and say, oh, yes, I'm going this way, and the other one goes, I'm going the other way, right? And so there's a concerted motion. And we're actually looking at more experiments where we can figure out where that happens and how that turns on and off, and which ones turn off and on at what temperature, if that makes sense, right? So it's not.
Yeah.
The other thing is it's not the same mechanism all the way throughout. We think there's different things that are different mechanisms, different arrangements that are happening as a function of temperature too.
Most of these processes, the way that it's absorbing the energy and the heat, they're not extraordinary, but given how this material is reacting to your research, the stability of it over these extremes is pointing to something else going on, as you were alluding to.
There's a couple of things, whether we're sensitive enough to detect it, right? And with the instrumentation we have at the moment, or whether, it's so concerted that we can't differentiate it, right? And so, so it's just we build up on research, and that's how research builds up. We know a little bit more, and then we build a bit more, and we build a bit more until we have a fuller picture. I mean, so just to give you an example, this material was worked on a few years ago, about 10 or 15 years ago, and what they found was a smaller range. They just worked on a smaller range, and they found this to be interesting, and so this is where we started our work, and we thought, well, let's look at bigger range as well. So it's an interesting material, and it's a sweet spot. So if you change the composition slightly, you get positive thermal expansion, so it expands up, or you get things that contract when you heat it up, which is called negative thermal expansion.
And while aluminium, tungsten, and oxygen are some of the elements being used to make this material, they're relatively common and easy to mass produce. The scandium, which also makes up this material, is rarer and therefore a little bit more expensive. I believe that you're working on trying to find a substitute for this to make this material worthwhile.
Yes. So scandium is more abundant than lead. Right, but the ores the ores are lower concentration, so you get higher concentration lead ores, so it's more economical to mine and process. However, scandium ores are lower concentration. Now that said, there's a lot of people working on trying to figure this out as well, and there's a few companies that are processing and making scandium material. So that is an avenue that we're going through too, but also replacing scandium with things like yttrium. And other sort of transition metals / rare earths / lanthanoids is another way to sort of go part. Working with the periodic table, we can actually do some compositional changes that may give us something very similar. However, there's been quite a fair bit of work in this space, and sort of getting that sweet spot might be quite hard.
Neeraj, where is this research taking you, and does it have a name yet?
It's a scandium aluminium tungsten oxide is what we call it. We didn't go through a name. Naming.
There has to be an acronym.
I'm a chemist, right? So yeah. Sorry, go ahead.
I was just going to say there has to be an acronym. Science and space love acronyms.
Not yet. ZTE is zero thermal expansion is what is the acronym for its property. We are looking towards it. So, we can make powders of it and we can make pellets of this material. So we're now looking at how do you process it, potentially to make films, to make things that you can then deploy, right? That's sort of one path of research. Another path of research is trying to understand pressure. So we've done temperature, right? So we know it's temperature stability, but you can imagine in different environments, pressure plays a role as well, right? So deep sea or even in space, when you sort of go in and out, there's a pressure difference. And we want to see how well this material absorbs pressure, right? So from a fundamental chemistry point of view, we're looking at how pressure doesn't show the same sort of properties as a function of pressure. And if it does, great. Or we can even send the bounds, this pressure and that pressure limits. And then we can also look at processing it. Because if we use it as a powder, it's not very useful. If we can make it a film, very useful. Or if you can process it in large quantities, very useful as well. So it's opened up quite a bit of research opportunities, and I'm looking forward to it.
Fantastic, Professor. It is one to watch. Neeraj, I really appreciate your time today. Thanks for beaming into Trekzone.
Thank you very much, and live long and prosper.
Keep up to date with Twitter. Catch new podcasts daily on YouTube. Plus, we're beaming to your favorite podcast app 5 days a week. Just search for Trekzone and subscribe.